quicker than the texture of space-time can stay aware of it, and it'll simply tear. I'm unnerved by this at present. Our night sky is changing quickly, and in simply a question of many years, if not sooner, it could turn out to be totally unrecognizable. Cosmologists overall are sounding the caution. Specialists like Neil deGrasse Tyson have recently affirmed the approaching blast of Polaris, and the story behind it is very alarming. Polaris, known as the North Star, has for quite some time been a constant in our night sky, filling in as a critical reference point for stargazers, pilots, and navigators. However, this could soon change, modifying our night sky and galactic estimations. We should dive into the meaning of this threat and its implications for us all. Join us as we uncover the account of Polaris as it approaches its end. For centuries, Polaris has guided sailors and astronomers alike, standing firm on a respected footing as a guiding light. Its steady presence in the night sky has been fundamental for navigation. Yet, this stability may soon be disturbed. In September 2023, a research paper presented by the esteemed Royal Astronomical Society cast uncertainty on the destiny of this divine light. Polaris is near the very edge of detonating, potentially disappearing from the night sky forever. Before we investigate the results of this disclosure, we should first learn more about Polaris, also known as the North Star or Pole Star. Polaris is unique because of its proximity to the celestial North Pole, arranged directly above Earth's North Pole. It appears practically fixed in the northern sky, found in the constellation Ursa Minor, or the Little Dipper. Polaris shines as a reasonably radiant yellow-white giant star, much larger and brighter than our Sun. It's not a singular star, but part of a complex triple star system, with Polaris A and Polaris B forming a binary pair, while Polaris C orbits around them. The interactions among these stars create gravitational forces, shaping their orbits and affecting their behavior. Any disturbances in these associations can lead to irregular variations in the star's brightness or pulsation patterns. However, the exact mechanisms behind these interactions remain unclear. Polaris is found roughly 323 light-years from Earth, meaning the light we see from it today began its journey more than 3 centuries ago. Subsequently, if Polaris were to detonate now, we wouldn't notice it until over 3 centuries later. The fact that Polaris has already made it even possible for it to have detonated, and we have yet to witness the light from that event. Over the course of time, the North Star has held enormous social, navigational, and symbolic importance. Its stability and fixed position made it a priceless guide for ancient sailors, directing them across oceans and lands. Symbolically, Polaris represented constancy and direction, staying immovable in the midst of the ever-changing night sky. For stargazers, Polaris served as a critical reference point, supporting the investigation of celestial movements in variable stars. As a Cepheid variable star, its periodic variations in brightness have provided important insights into cosmic properties and the nature of variable stars. This characteristic also played a key role in determining vast distances and calibrating instruments. These pulsations follow a predictable pattern, which has been the norm for the star, making it easy for us to anticipate its behavior. However, recently Polaris has wandered from this normal behavior. This anomaly in its pulsation cycle has puzzled cosmologists, prompting a closer assessment of this divine inconsistency. Rather than its standard, predictable pattern, Polaris has begun showing irregular patterns of dimming and brightening. Researchers are now raising concerns that the star might be approaching the end of its life. This aligns with behaviors often seen in stars nearing the end of their life cycles, such as the steady prolongation of Polaris' pulsation period, which, when stable, was only a minor variation. Now, we've noticed an annual increase in its pulsation period of 4.5 seconds, which may seem insignificant but holds important implications. Some cosmologists suggest that gravitational interactions between the stars in the Polaris system could be causing these fluctuations in its atmospheric conditions, directly affecting its pulsation patterns. However, others are more alarmed, believing that the star is nearing the edge of exploding. The similarities between Polaris behavior and that of Betelgeuse, another prominent star in the Orion constellation, are striking. Both stars have shown puzzling anomalies in their brightness, raising concerns about potential explosions. Stars in their dusk phases often display such irregularities before reaching the climax of their life cycles. While NASA has expressed heightened concern about Betelgeuse, similar attention has not yet been formally directed toward Polaris. However, as a Cepheid star approaches the end of its life cycle, it advances through various stages, including the main sequence stage, the red giant stage, and ultimately the supernova explosion. Based on Polaris' irregular pulsations, researchers predict that it has entered the stages of helium exhaustion, typical of stars approaching their end. These abnormalities in Polaris behavior align with patterns characteristic of Cepheid stars in their twilight stages, though conclusive signs of its impending supernova remain uncertain. Astronomers are steadily investigating these anomalies to understand Polaris' destiny. If Polaris were to go supernova, it would likely be a breathtaking event in our sky, potentially dominating the moon and becoming one of the brightest objects visible for days, weeks, or even months. Its appearance could radically change, briefly altering our view of familiar celestial bodies like the Big Dipper or Ursa Minor, of which Polaris is a part. Rest assured, Earth would likely be completely safe, even if Polaris were to explode, given its mass and distance from us. While a Polaris explosion might not be as visually spectacular as Betelgeuse's, it could still be visible to the naked eye for an extended period and outshine nearby stars. Astronomers and observatories would undoubtedly take notice, sparking interest within the academic community and among stargazers worldwide. However, the specific visibility and impact on Earth's environment or atmosphere would likely be less significant compared to a closer supernova event. But what about Polaris itself? What will be its destiny after a potential supernova event? We should clarify one thing. While giant stars normally end their lives with a supernova explosion, this is unlikely to be the case for Polaris. When a massive star goes supernova, a tremendous explosion occurs within it, marking the final catastrophic stage of its life. This process involves a complete collapse of the core, triggering a powerful shockwave that causes the star to explode violently. However, Polaris isn't massive enough to undergo such an explosion. Instead, when Polaris exhausts its nuclear fuel, it will shed its outer layers and transform into a white dwarf. This transformation won't lead to a supernova but instead a peaceful end, as it evolves into a small, incredibly dense stellar remnant. A white dwarf is the remnant of a low or medium-mass star that has exhausted its nuclear fuel. It's extremely dense, about as massive as the Sun but compressed to the size of Earth. When this happens, we will no longer be able to see its remnants from our planet, much like we no longer see the star today. Comparing the potential effects of Polaris explosion with historical supernova events offers valuable insight into the development of stars and their ultimate fates. Comparing our expectations with well-documented supernovae like SN 1054, SN 1987A, and later events such as SN 2011 Fe or SN 2014 J provides important data for understanding the potential outcome of Polaris burst. For instance, SN 1054 resulted in the formation of the Crab Nebula, a nebula that continues to expand and emit radiation across numerous frequencies, offering astronomers a rich field for study. Likewise, SN 1987A, observed in the Large Magellanic Cloud, provided insights into the processes of nucleosynthesis and the dynamics of supernova remnants. Studying phenomena like the formation of nebulae, emission of cosmic rays, and changes in brightness can offer clues about Polaris' unique properties. The development of nebulae like the Crab Nebula results from the ejection of material during the supernova explosion, which interacts with the surrounding interstellar gas and dust, enriching it with heavy elements and contributing to the process of cosmic birth and death. Moreover, the release of cosmic rays and high-energy particles accelerated by supernova shock waves has implications for astrophysical processes and radiation conditions. To make a definitive comparison, scientists assess differences in mass, production, and speed of ejected materials between Polaris potential explosion and other observed events. This includes analyzing light curves, spectra, and remnants from these events and projecting similar characteristics for Polaris expected burst. Researchers are also evaluating whether Polaris burst could lead to the formation of nebulae or specific elemental distributions, enhancing our understanding of its potential outcomes. Another important area of research involves assessing the pulsational variability of stars approaching their end stages, like Polaris, against observed supernova progenitors. This comparative analysis can help identify similarities or deviations, offering insights into the burst mechanism. Pulsational variability in stars approaching the end of their lives might indicate internal instability or impending catastrophic events, offering clues to the evolutionary processes leading up to supernova explosions. Despite careful observations and extensive analysis, astronomers remain puzzled by the anomalies observed in Polaris behavior. Unraveling the unique circumstances driving these anomalies holds the key to advancing our understanding of stellar evolution. Determining the mechanisms responsible for Polaris irregular pulsations requires interdisciplinary collaboration and the development of advanced theoretical models and observational techniques. The potential loss of Polaris as an essential reference point in the night sky presents significant concerns for astronomical endeavors. Ground-based telescopes and celestial measurements would need recalibration, affecting the accuracy of cosmic assessments. The absence of Polaris could also influence navigation systems and cultural practices dependent on celestial landmarks, highlighting the importance of this celestial event. The mysterious behavior exhibited by Polaris emphasizes the need for deeper investigations and dedicated research efforts. Astronomers must grapple with the complexities surrounding its unpredictable pulsations and present tangible solutions. Recognizing the importance of advancing our understanding of cosmic phenomena, the quest for answers about Polaris' fate remains ongoing. Ultimately, the resolution of Polaris' destiny remains uncertain, and only time will reveal its true nature. Regardless, the pursuit of knowledge and understanding, despite immeasurable uncertainty, stands as a testament to humanity's enduring curiosity in unraveling the mysteries of the universe. As astronomers continue to monitor Polaris, the star's unusual behavior prompts a broader evaluation of similar celestial anomalies. The study of other Cepheid variable stars, particularly those showing signs of irregular pulsations or strange dimming and brightening cycles, is crucial. By examining these stars, researchers can gain insights into the mechanisms driving such inconsistencies and their potential consequences. Observations of these stars can help refine models of stellar evolution and provide more accurate predictions about the life cycles of stars like Polaris. Furthermore, advancements in technology and observational techniques play a vital role in these studies. The development of more sensitive telescopes and space-based observatories allows for more precise measurements of stellar brightness and pulsation patterns. This technological progress enables astronomers to detect subtle changes in stars that were previously inaccessible, leading to a better understanding of their behavior and potential fate. Another aspect under investigation is the role of interstellar conditions in shaping the behavior of stars approaching the end of their life cycles. The interaction between a star's outflow of material and the surrounding interstellar medium can influence its observed properties. Studying these interactions helps astronomers understand how a star's environment may impact its evolution and eventual transformation into a white dwarf or supernova. Moreover, the impact of a potential Polaris explosion on other celestial bodies and cosmic phenomena is a topic of interest. The shock waves and material ejected from such an event could influence nearby stars, planetary systems, and even the formation of new celestial objects. Understanding these potential effects provides a more comprehensive view of the astronomical cycles at play and highlights the interconnectedness of various cosmic events. The scientific community remains committed to unraveling the mysteries surrounding Polaris and other celestial phenomena. Collaborative efforts across institutions and disciplines are essential for advancing our knowledge of the universe. The quest for answers about Polaris' fate and the broader implications of its behavior underscores the importance of ongoing research and the drive to understand the dynamic and ever-changing cosmos. In addition to studying individual stars like Polaris, scientists are also focused on improving theoretical models that describe the life cycles of massive and variable stars. These models integrate data from a range of observational sources, including ground-based telescopes, space observatories, and laboratory simulations of cosmic conditions. The combination of diverse datasets helps refine our understanding of the processes governing stellar evolution, including the complex interactions within binary and multiple star systems. Astrophysicists are also investigating how cosmic explosions can impact larger-scale phenomena, such as galaxy formation and the distribution of heavy elements throughout the universe. Supernovae, including those from stars like Polaris, play a critical role in enriching the interstellar medium with elements necessary for planet formation and life. By studying these events, researchers hope to gain insights into the life cycles of galaxies and the chemical evolution of the universe.